Hi everyone. Here we go to the next topic, inverse Laplace transforms. So here the definition of inverse Laplace transform. If L of f of t equal to f of s, then f of t is known as inverse Laplace transformation of f of s, where L inverse of f of s equals f of t, where L inverse was known as inverse Laplace transform operator. So if here L of f of t, that means Laplace transform of f of t equal to f of s, then its inverse, that means L inverse of f of s is equal to f of t. So this is the definition for the Laplace transform. So here are some inverse Laplace transform of some elementary functions. So here we know that here L of 1 we know that 1 pi s. That means Laplace transform of 1 is 1 pi s. So L inverse of 1 pi s will be 1. Similarly, Laplace transform of t equal to 1 pi s square. So L inverse of 1 pi s square equal to t. Then L of t raised to n is n factorial by s raised to n plus 1. So L inverse of 1 pi s raised to n plus 1 equals t raised to n by n factorial. Then L of e raised to at is what 1 pi s minus a. So L inverse of 1 pi s minus a equals e raised to at. Now L inverse of 1 pi s square plus a square equals 1 pi a sin at. Then similarly we can prove these conditions. L inverse of s by s square plus a square equals cos at. L inverse of 1 pi s square minus a square equals 1 pi a sin h at. L inverse of s by s square minus a square equals cos h at. L inverse of s square minus a square by s square plus a square whole square equals t cos at. L inverse of s by s square plus a square whole square equals 1 by 2a t sin at. So these are some important inverse Laplace transforms of some elementary functions. So using this we can do problems. Now we go to the theorems. So here the first theorem is, if L of f of t equals f of s, then L of g of t equal to g of s, then L inverse of a into f of s plus b into g of s equals a into L inverse of f of s plus b into L inverse of g of s. That means here is the linearity property of inverse Laplace transform. Here in the linearity property in Laplace transform we have already done. Same way we can apply the linearity property in inverse Laplace transform. So L inverse of a into f of s plus b into g of s is same as, take the constant part outside. So a into L inverse of f of s plus b into L inverse of g of s. So this is the first theorem, that is linearity property for inverse Laplace transform. Now we go to the next theorem, that is shifting theorem for inverse Laplace transform. In Laplace transform we know the shifting theorem, that what if L of f of t equal to f of s, then L of e raised to at into f of t equals f of s minus a. So in the case of shifting theorem Laplace transform, this property we have already studied. So Laplace transform of f of t is f of s. There you replace s by s minus a. That is what Laplace transform shifting theorem. Now in the case of inverse Laplace transform, we can take L inverse of f of s minus a equals what e raised to at into f of t. That means in order to find the inverse Laplace transform of f of s minus a, here you multiply by e raised to at and multiply by Laplace transform of f of s. So here L inverse of f of s minus a equals e raised to at into f of t. Now we go to some examples using these formulas of inverse Laplace transform. The first problem is to find L inverse of 1 by s raised to 5. We know that L inverse of 1 by s raised to n plus 1 equals t raised to n by n factorial. So substituting for n equal to 4, here we will get t raised to 4 by 4 factorial, that is t raised to 4 by 24. So this is the answer. Next we go to the L inverse of 1 by s plus 2. Here we know that L inverse of 1 by s plus a is e raised to minus at. So here L inverse of 1 by s plus 2 is e raised to minus 2t. Now L inverse of 1 by s square plus 4. That is L inverse of 1 by s square plus a square is 1 by a sin at. Here a is root 2. So here we will get, here a is 2. So here we will get 1 by 2 sin 2t. Now we go to the next example, L inverse of s by s square plus 9. Here we can apply the property L inverse of s by s square plus a square equals cos 80. Here in this problem a equal to 3. So here L inverse of s by s square plus 9 equals cos 3t. Next, L inverse of 1 by s square minus 4. That is, L inverse of 1 by s square minus a square is 1 by a sin h8. Here a equal to 2. So 1 by 2 sin h2t. Now L inverse of s by s square minus 2. Here L inverse of s by s square minus a square is cos h80. Here a is root 2. So here we will get L inverse of s by s square minus 2 equals cos h root 2t. Now we go to the next problem. Find L inverse of 3s plus 2 by s square plus 9. Before directly applying the L inverse Laplace transform, here you can apply the linearity property. That is 3 into, split here. So 3 into L inverse of s by s square plus 9 plus 2 into L inverse of 1 by s square plus 9. That is equal to 3 into a equal to 3. So cos 3t plus 2 into here 1 by s square plus 9 inverse Laplace transform is 1 by a sin 80. Here a equal to 3. So 1 by 3 sin 3t. So here we got the value of L inverse 3s plus 2 by s square plus 9. We got the value to 3 cos 3t plus 2 by 3 sin 3t. Next problem is to find L inverse of 3 by s minus 2 whole raised to 5. So here we know that we can apply shifting theorem. That means instead of s it is s minus 2. So instead of s it is s minus 2. Here we can apply the linearity property 3 into L inverse of 1 by s minus 2 whole raised to 5. Here instead of s it is s minus 2. So here you replace e raised to 2t or multiply by e raised to 2t. So 3 into e raised to 2t into L inverse of 1 by, and then instead of s minus 2 you can replace as s 1 by s raised to 5. That is same as 3 into e raised to 2t into t raised to 4 by 4 factorial. We know that 1 by s raised to 5 inverse Laplace transform is t raised to 4 by 4 factorial. So here we got the value 3 e raised to 2t t raised to 4 by 24. That is, you can cancel 3 and 24. Then we will get t raised to 4 e raised to 2t by 8. Okay. Thank you.